As we have talked about in class, there are a number of ways that we can construct our shear force and bending moment diagrams for a beam. Those three are in particular would be the graphical approach, would be the integration approach, and lastly drawing our FBDs and obtaining expressions for V and M, the function of x from those. On this problem 9.4, we have a beam which is pinned over on the left side at A. There's a roller connection there at B, and there is a 2,000 Newton force on the right end C. There's a distributed load of 2 kilonewtons per meter downward between A and B. And so if we want to find the shear force bending moment diagram for this beam, we need to choose which method we're going to use. Well, we've already either worked this problem in lecture, or there's a solution video for this using the graphical technique. What I would like to do in this example is work it through both the free body diagram approach and the integration approach, just to verify that we get the same approach, and importantly to see the differences among these three different groups. Whatever method that we use of these three, it all depends on drawing the correct free body diagram and determination of the external reaction forces on this beam. So let's do that first. We know that the support over there at A will have a vertical component, which we'll call AY. Same way here with the roller connection there at B. There is a distributed load that's acting between A and B. We know that the resultant of that is going to be 4 times 2 are 8 kilonewtons. And we have the external force of 2 kilonewtons acting there on the right side there at C. What I'm going to do is use for my force and moment calculations a set of coordinate axes that are shown here, x to the right and y up. This way, by the right-hand rule, z is coming out of the screen. First equation I'm going to write down is the summation of moments about end A of this beam. We have the reaction force By has a moment arm of 4. It's in the plus z. We have the resultant force there, 8, has a moment arm of 2. It's in the minus z. And then the 2 kilonewton force on the right-hand side, it has a moment arm of 6. It's going to be in the negative z. For equilibrium, that sum is equal to 0. From this, we see that By, the reaction at y, is 7 kilonewtons. In order to find Ay, what we do here is sum forces in y. We have Ay plus By are two reactions. We have the resultant force of negative 8 and the concentrated force there of minus 2 there on the right side. For equilibrium, that is 0. So from this, we see that the reaction force at A is 3 kilonewtons. And both of these have a plus sign in front. And what that means is the direction that we chose for AY and BY in the beginning was correct. So the first approach that I'm going to take is one where we use directly our FBDs. I'm going to break it up into two parts. Section AB will be the first part, and section AB, of course, is between the values of 0 and 4 for x. So what I do here is I draw a free body diagram of a part which is somewhere between A and B. So here it shows the full length of the beam. What I want to do is draw a free body diagram of a section here. This is A, and B is over here. So this cut that I'm making through here is at the value of x. So the forces that I have acting on this FBD is going to be the applied force AY. There's going to be a shear force V on the right face. It's positively down, so I'm going to draw it that way. And the bending moment on the right face is positive in a counterclockwise sense, so I will draw it as that. There's also this resultant of the distributed load, and since it's a force per length of 2, it's over a length of section called x. It's going to be a force downward there of 2x. When I sum forces acting in y, I've got AY minus V minus 2x, and for equilibrium that is a 0. So from this, I see that the shear force as a function of x is equal to AY minus 2x, so that's 3 minus 2x. So between A and B, that is the shear force. To get the bending moment there at value of x, I do my moments about A, that's my choice. We got the concentrated or the resultant force there of 2x. It has a moment arm of x over 2, halfway there in the middle. It's in the negative z. We have the shear force V. It has a moment arm of x, and it's going to be in the negative z, so I put a negative sign there in front. Of course, the bending moment M for equilibrium, that is a 0. So in the end, the bending moment M will be equal to V times x, whatever we got, plus x squared. V of x is equal to 3x minus 2x squared. Add on to the x squared. So the shear force as a function of x is 3x minus x squared. I'm sorry, I said that wrong. The bending moment is 3x minus x squared. So that's what we have in section AB. If we're looking for section BC, section BC is between the value of 6, between 4 and 6. And for this, I need to draw a new FBD. So the new FBD is going to be for a section that terminates on the right side somewhere between B and C. So this is what we've got here. This is going to be between there and there. Oops, let me try that one more time here. I need to make sure that it's clear. So here's the whole beam. We're going to be taking just a section like this. So this is A. B is somewhere here. This is C on the end. The forces that we have acting on this, there's going to be the reaction force of AY at A, reaction force of BY there at B. We know that between A and B is the distributed load. It's going to have a resultant of 8 kilonewtons down. There's going to be a shear force V acting there at the cut, a bending moment there of M. Again, this cut is being made at a position that we're labeling that as X. So from this, when I sum forces in Y, I get AY plus BY minus 8 minus V, and for equilibrium that is a 0. So the shear force as a function of X then is going to be AY plus BY minus 8. Adding all those numbers together, we get 2. And between B and C, the shear force is a constant value there of 2. When I sum moments about A, what I got here is the resultant force 8 is a moment arm of 2. It's in the minus z. I have by, which has a moment arm of 4. The moment is in a positive z. I have the shear force v, moment arm of x. It's in the negative z. And then, of course, the bending moment at the cut, which is m. So the bending moment in that section as a function of x is going to be equal to 16 minus 4 by plus v times x. And so what I end up with here is a minus 12 plus 2x. So that's the bending moment at a cut between B and C as a function of x. So this is what we get for shear force and bending moments along the full length of the beam by using our free body diagrams. I'm going to do the same thing by integration. Note that the graphical approach is based on the integration idea, but here we're actually going to do the integrations rather than just using it as a guide for constructing V and M. So section AB, again, this is for values of x between 0 and, let me make sure I got this right, between 0 and 4. And in that section, we start out by knowing the distributed load P. That is a minus 2, which is a constant. We know that V of x is going to be equal to V at x equal to a 0 plus the integral from 0 to x of P of x dx. We know that the shear force on the left face, that was equal to AY, it's up, so it's a positive 3, minus 2x. 2 is a constant. And this is what we had by our FBD approach. Our moment expression. That's the moment at x equal to a 0, plus the integral from 0 to x, the shear force, is a function of x dx. We know on the left face there was no bending moment applied, so m at x equal to a 0 is a 0. All we have left here is an integration from 0 to x, 3 minus 2x. In that integration, that gives us 3x minus x squared, and that's exactly the same thing that we got by using our FBD approach. If I now look at section BC, and that would be for x between 4 and 6. Here, the distributed load P is a 0, so V of x is going to be V at 4 plus the integration from 4 up to x of P of x dx. Well, one thing that I needed to know is what is V actually at 4 plus. It's just to the right of that concentrated load there of By. So what I really need to do is do an aside here and say that at B I have to take into account this jump. That is, the shear force just to the right of 4 is equal to the shear force just to the left of that position plus By. This is our rule that we had whenever we have a concentrated force. So we know that right to the left of 4, we calculate V as being 3 minus 2 times 4. So this is the shear force right to the left of By. Add on to it By, which is a 7. So this ends up being a 2. So I do this in order to get this value here. We know that between 4 and 6, there's no distributed load P. So what we end up with is that v of x over on the right-hand segment of the beam is a 2, which is a constant. And finally, when we do segment BC, I don't need to write that down again, do it, because I already have. I need to have m of x here is equal to m, what it is at 4, plus the integration from x to 6 of vx dx. This is just using the integration results that we have. We know that m at 4, that's equal to 3 times 4 minus 4 squared. This is what we got from the last result. And on this side, we have integration from 4 to x of the constant value there of 2. And so when we get through, when we do all the calculations, we end up with minus 12 plus 2x. And the great thing about this is the same thing that our FBD approach gave. So in this example, what we're doing is trying to illuminate the differences and similarities among our 3 different approaches for getting shear force and bending moment diagram. The graphical approach, we've done that. This one here is focusing on how the FBD approach works and how integration works. It would seem like, just from this one example, that likely the integration approach is better than the FBD because it's less work. We don't have to draw a number of FBDs along the way. What we simply need to do is be able to do these integrations. The graphical approach is one which is even simpler than this because it doesn't really require us to do the integrations. For simple loadings as this, we can readily use our rules in order to construct that. But whichever method that you use, totally up to you. You need to make up in your mind which method you think is the best.